All right, class, let's start section 1.4. So, as I said, we're just going to continue with the rules for derivatives, and we're just simply going to make the functions, or in other words, our expressions, more and more complicated. So, the product and the quotient rules are next. So we already saw how we're supposed to take derivatives of a sum or difference, right? That was super easy. You just simply go term by term, right? Easy, okay? Unfortunately, a product or a quotient, the rules are not going to be the same. So as you see already from here, if you take the derivative of a product, you don't just go and take the derivative of each of the factors, okay? This right here is the product rule. So it's not as easy, but we're going to get through it with a lot of practice. So as you see from the formula here, we're just going to jump right into it. We're not, again, we could prove these formulas with the limit definition, by the way, but it's just really not an issue. In business calculus, in a calculus class, you will go through the formal proof of why that looks like that. We're just simply going to practice on it, okay? So take my word for it, that's how you take the derivative of a product. Okay, so what does this rule seem to say is that when you take the derivative of a product, this is what you do. You take the derivative of the first term, or the first factor, I'm sorry. Okay, so F is your first, G is your second factor, okay? So you take the derivative of the first factor times the second factor on change, as it is, plus, what do we do next, right? Then plus, leave the first factor as it is, times the derivative of the second factor. So basically what we're doing is we're taking the derivative of one factor at a time. Now mind you, if you were to have the product of more than two factors, f something times something else, you take the derivative of one factor at a time. So let me write this down. If we should have more than one factor, I'm sorry, more than two factors, we basically take the derivative of one factor at a time. Sorry about my handwriting, it's just so hard to write as I'm squished in here. Okay, so just to show you guys, this is how I'm filming. Ta-da, I have this tower right next to me, and then I have this paper, and then I put this on my cooking rack, and I set it this way, and then I only have about this much space to write, so it's hard, but it's the best I've found, best method. Okay, all right, so there it is. So we'll practice, okay, I promise. Now the quotient rule looks even worse. So as you see, you have a fraction between two expressions. So the formula says, what are we going to do? Let's take it apart, and then we're going to, I'm going to write this down. So if you take the derivative of the quotient between two expressions with x's, what are we going to do? you're gonna take the derivative of the top one times the bottom factor. Then minus, leave the top factor alone, times the derivative of the bottom factor. The whole thing divided by the denominator, not the derivative, right? The denominator as it was, squared. So quite a bit. So what do? Take the derivative of the top, times the bottom, minus, take the derivative of the bottom, times the top. The whole thing over the bottom squared. So your whole bottom squared. And that's what it is. Okay. Now, not easy, but again, with a lot of practice, we're going to get through. So let's just practice right away. Here it is. Find the derivative of the following functions. Okay, no problem. So, y prime. Now I have the product of two factors, yes? This is my first, this is my second factor. So the derivative says, take the derivative of the first factor. So what's the derivative of 2x plus 3? Well, the derivative of 2x is 2, yes? And then the 3 goes to 0. So the derivative of the first is 2 times, leave the second one alone, plus, leave the first one alone, times the derivative of the second. What's the derivative of 3x minus 1? Well, that's just the 3. Okay, great. So again, one thing at a time. The derivative of the first, leave the second alone, plus take the derivative of the second one, leave the first alone. Okay, what we're going to do is distribute this because we're going to simplify it. So distributing, I'm going to get a 6x minus 2 plus 6x plus 9, which combines for a total of 12x plus 7. That's the derivative, right? I wrote it down. There we have it. Now, the good news is, for the most part, we can avoid using the product rule. Why? For now. Because we're dealing with algebraic expressions that can be multiplied. So by the time we get to chapter 3, when we'll talk about exponential and logarithmic functions, you can add a logarithmic function to an algebraic expression, right? And so, or an exponential to an algebraic. So then we will definitely need the product rule. But what I'm saying is, I can avoid this. How? Well, by multiplying it first, right? We actually did that in the last section. There was an example where it was actually a product. I think it was the revenue function in the last example, and we were like, we don't even know what to do with the product, so let's just multiply it out. Well, the same thing here, whether you know how to deal with it or not, since the product rule takes quite a bit of time, if we can avoid it, well, we will. So how do I avoid using the product rule? Well, by not having a product. In other words, multiply this out. So that's simple algebra. So 6x squared minus 2x plus 9x minus 3, which combines to a 6x squared plus 7x minus 3. Okay, so all I've done is I still have my function, right? I'm not finding the derivative. I just rewrote my function by multiplying it out. So now what's the derivative of this function? Okay, according to what we learned in the last section, if you just have a sum or difference, you just go term by term. So what's the derivative of 6x squared? It's 6 times the 2 that comes down, which is 12x, plus the derivative of 7x is 7. And of course, the derivative of negative 3 is 0. So did we get the same answer? Oh, yeah. Okay. So again, if we can avoid using the product rule, we absolutely will. Okay. So let's look at this next problem. Can I actually multiply this 2x to this radical? In fact, we can. How? By rewriting this radical, which we anyways would have to, into an exponent, right? So we would have to do that anyways to use the power rule. So what is that? It's a 2x times, what does the 6 root of x to the 5th look like? It's an x to the 5 divided by 6. Now, can I put these x's together? Sure. We've learned rules of exponents that say what? When you multiply numbers with the same base, what do you do with their exponents? You add them up. So 1 plus 5 over 6, well, it is 1 and 5/6, but that doesn't look too pretty. But 1 is the same thing as 6/6, so that's 11/6, right? And look at that. I have no product anymore, so now I can easily just simply go ahead and take the derivative. So what's the derivative of this? Is 2 times, using the power rule, the 11 over 6 comes out, x to the 1 less than 11 over 6, and when you take 6 over 6 back out of 11 over 6, you're left with 5 over 6. So this reduces to 11 over 3 times x to the 5 over 6. Okay. Now, what I'm going to do is show you how we could have gotten to the answer if we did use the product rule. So I'm going to take it from here. Anyways, as I said, you would have had to rewrite this radical into a rational exponent. So here's your first factor, here's your second factor. So the product rule says take the derivative of the first factor, that's a 2, times, leave the second factor alone, plus, leave the first factor alone, times the derivative of the second factor, which is 5 over 6, x to the 1 less than 5 over 6 is negative 1 over 6. Okay, so that's a 2x to the 5/6 plus multiplying these out, right, these two terms, so 2 times 5 over 6 is 10 over 6. And then how again do we put these x's together? By simply adding their exponents, yes? So 1 plus negative 1/6, in other words, 1 minus 1/6 is 5/6. So as you see, we have like terms here. The variable have the same exact exponents. How do we put them together to get more x to the 5/6s? By adding their coefficients. So 2 plus 10 over 6 is 1222 over 6, which reduces to, of course, 11 over 3. And that kind of helps because I already had that answer. So again, as you see, it really, really helps to multiply first. We had to use the same rules here as we had to, in other words, what? Multiplying numbers with the same base, right? By adding their exponents. We had to use that rule right here as well, yes, plus some more, and the product rule. So what I'm saying, again, is if we can avoid using the product rule, we'll definitely do so. Okay, so if you can multiply first, great. Okay, even more proven is in this example here. Do you know how to multiply these type of parentheses, binomials? Sure, you've gone through a lot of algebra, okay? So what I'm going to do is I'm going to simplify this first by multiplying it out. So I'm going to distribute square root of x times square root of x is x. By the way, you could even avoid some of this. I'll tell you in a minute. Minus 3 square root of x plus 3 square root of x and minus 9. And what could we have avoided? If you recognize this is one of those special products where you multiply the sum and the difference between the same two terms, excuse me, you're left with just the product of the firsts plus the product of the last, right? The O and I in these products always cancels out. Okay, which is also why we use it as a trick for simplifying so many other expressions, such as what? Rationalizing denominators or numerators, right? We use this trick in 1.1. Okay, but there you go. There's my function. Rather than dealing with radicals, product rules, rational exponents, right? All of this, just the simple multiplying of these two binomials turned my function into a super, super nice and easy one. So now, could you just tell me what's the derivative of it? 1. Why? Because the derivative of x is 1 minus the derivative of 9 is 0. That's it. So if you would have gone through the trouble of using the product rule, rewriting x square root of x as an x to the 1/2 and all of that, and then simplify the whole thing, you would end up with 1. Okay. All right. So, of course, your question will be, can I do that every time? Yes, you can. Okay. You can definitely first multiply out if you can, right? If it's possible. Some things will not be possible. You won't be able to multiply everything. As I said, by the time we get to, let's say, chapter 3, and you have an expression like this, these are different types. You can multiply them out. So how will you take the derivative? Well, you're going to have to use the product rule. There's no avoiding it. But for now, for the very most part, yes, you can. Okay. All right. Now, next one's the quotient rule. And there's no, I mean, there is. I shouldn't lie. On the next page, we'll be able to overcome the quotient rule. But again, how were we able to not use the product rule? Because we, in fact, were able to multiply first, right? So simply being able to distribute first, we turn our product into a sum, and that was much, much easier to deal with, right? Now, can we divide these two binomials? The answer is no, okay? You could use long division, but that's not going to help because you'll still end up with a fraction as a remainder. So you could try long division. X plus 1 goes into x minus 1 one time, and then there's a remainder of probably 2. So it's not going to work out, okay? Sometimes we can do that. We could factor the top, factor the bottom, reduce. Yes, we can do that, but there's nothing to factor here. So, unfortunately, the quotient rule, which, by the way, is the uglier of the two, sometimes we cannot avoid it. But if we can, we will definitely do so. Okay, so what's the derivative of this function? Now, when you look back at the formula, there's things about the top of the fraction and things about the bottom of the fraction. So the formula says you're going to take the derivative of the top. What's the derivative of the top? 1. Times, leave the bottom as it is. And don't forget, this time it's a minus. Leave the top as it is, times the derivative of the bottom. And the derivative of x plus 1 is 1 plus 0, so 1. Okay, over the whole thing divided by the bottom squared. Okay, there's the formula. So, here, this is what I'm going to do. this one here is the derivative of the top times the bottom minus, leave the top as it is, times the derivative of the bottom. Okay, times the all over the bottom as it is squared. Okay, so that's what we came up with. Okay, so I'm going to simplify that. So 1 times x plus 1 is x plus 1 minus 1 times x minus 1. So don't forget distributing the minus. So it's a minus x plus 1 all over the bottom squared. So the x's are going to go away, and I'm left with 2 over x plus 1 squared. And there it is. That's your answer. Okay. All right, so, okay, well, there's another one for you. Can we divide these? Again, you could use long division if you remember that's a beast in itself. Maybe we could factor, in fact, the bottom, as you see. It's an x minus 3 times an x minus 3, but the top is non-factorable, so there's nothing we can do. So we're just going to use the quotient rule, right? We're asked to find the derivative. So, a long thing. Take the derivative of the top, okay? So what's the derivative of the top? Is going to be a 6x squared plus 5, right? Times the bottom as it is. X squared minus 6x plus 9. Then minus, leave the top as it is, times, take the derivative of the bottom. So the derivative of the bottom is 2x minus 6. All over the bottom squared. Now, of course, we would have to distribute that whole top, combine like terms, and so on and so on. But on a problem like this, I would not make you simplify it. Okay, just leave it. It's too much. The point of all these problems is not to test if you know how to distribute, right, long things, but to see if you can simply understand the derivative of the top times the bottom minus the top as it is times the derivative of the bottom, and so on. So this is all I'm testing. On a problem like the one prior, yes, it just took another 30 seconds to simplify, so it's not a big deal. So on a test, if I should give you a problem like this, it would say in parentheses, do not simplify your answer, okay? So you don't need to touch it. If it doesn't say do not simplify, then yes, distribute, combine. It's just too much though, okay? So again, the point of it is if it gets too complicated, I don't need you messing with this because that's not the point, right? If it's simple enough, then yes, go ahead, okay? All right, now of course, why would we want to find derivatives? Because there's something to do, right, with these derivatives. We put them to good use. So yes, if it wasn't a problem where you had to now identify, I don't know what, interpret some answer, then you would need to simplify, right? But again, a problem like this would not come up in a situation like that, where you would need to actually go on and do something else. By the way, just in the next section, we'll learn to take the second derivative. So take the derivative of this, that's insane, right? So again, if I don't find it necessary for you to simplify it any further because that wasn't the point of the problem, I will say so. Okay, now let's look at this one here. Can we simplify this? The answer is yes. Can I avoid using the quotient rule this time? Yes. And the reason for it is because I'm dividing by one term only. And when we divide by one term only, we can very well distribute that one term. That's how you divide by what we call monomials. you distribute to each one of the terms in top. Can I do that here? Yes, but 2x cubed divided by this whole thing, I still couldn't reduce anything, right? Because you still have a bunch of pluses and minuses. So, again, algebra is quite necessary for all of this. All right, so knowing that I only have one term, right? Again, if I ask you to basically subtract these two fractions, well, how do you do that? Well, since we have a common denominator, we keep that denominator and just subtract the tops, right? So it's just the reverse process to adding, subtracting fractions. So now I can reduce. Why? Because I just have products. There's no pluses or minuses left in this fraction. So 3x to the fourth divided by x squared. If you remember from your rules of exponents, you simply subtract, right? When you divide numbers with the same base, you subtract the exponents. Okay, same thing here. Dividing numbers with the same base, you subtract their exponents. So 3 minus 2 is a 1. Well, that looks like a whole lot nicer thing to take the derivative of. Okay, and that's just because it was one term only on the bottom. So the derivative of these two terms now is simply 6x minus 5. Okay, so again, do not continue on writing equals to 6x minus 5. It's not the function, right? The derivative is equal to that. Okay, so please be careful on your notation. Okay, so what I have you in this last example is both a product and a quotient. Could we simplify this? We can divide. We could simplify by putting this over 1 and distributing the tops. That way at least I only have a quotient rather than a product and a quotient. But my reason for giving you this problem is to practice one more time on both. So we're going to have to use the product rule and the quotient rule. Okay, so here it is. The derivative of y, first of all, it's a big product, right? That's your first factor. That's your second factor. So the product rule says take the derivative of the first, which is 5x to the fourth, right? Power rule, plus the derivative of x is 1, times, leave the second one as it is. Okay, so one more time. That's the derivative of the first times the second one, right, as it is, no derivative. And then it says further on in the product rule, plus, leave the first factor alone, times concentrate on taking the derivative of the second factor. Okay, now the second factor is a quotient, so to take its derivative, we need to use the quotient rule. So the quotient rule says to take the derivative of the top. Yes, so again, I'm concentrating on this alone. Take the derivative of the top, which by the way is just 3x squared, times the bottom, minus, leave the top alone, times the derivative of the bottom, which is just the 1, right? Because the derivative of x is 1, plus the derivative of 2 is 0, all over the bottom squared. Now, definitely, I don't want you simplifying this. It's just to practice on the mechanics of the rules, right? First times the second, and so on, tops versus bottoms. So I just wanted to go through the structure of the product and the quotient rule. So again, this would be one where I'm saying leave it, just show me you know the rules. Okay, all right. Okay, so we might get this done, even though it's going to be a little bit longer video, into one video only for this section. Okay, so as an application of quotient rule, we're going to talk about average cost or an average revenue and profit. So average cost or average revenue or average profit, simply means to take the total cost and divide it by how many items you have. So the average cost is simply the cost function divided by the number of items. So let's say, and basically what it is you're splitting, and yes, there's an average revenue and an average profit, but mostly this problem is about average cost. Why? Because your cost is made up of two things, as I said, a variable cost and a fixed cost. So let's say you are, and there it is, there's a problem right here on the next page. Say the cost of producing X items is 5X plus 300. What does that really mean? 300 is the fixed cost. Why? Because if you produce 0 items, right, you've done nothing. You haven't produced a damn thing, a thing. Then what's your cost, right? Plugging in a 0, 300. So before you even started producing anything, right, any items, you had some costs of 300. From what? Machineries, right, the tools you have to use, maybe the space you have to use, whatever it is, but that's a fixed cost, right? You haven't done a thing yet, okay? And then 5 is the variable cost. In other words, what? For each single item you're producing, you're adding on another $5 to your cost. So as you see why it's also called variable cost, because that term has a variable in it. So if you produce 0 items, as I said, your cost is 300. If you produce 1 item, your cost is 305. If you produce 2 items, your cost is 310. So every time you add on an item, you add another $5 to your cost, right? So 5 is the variable cost, or the cost per item, yes? Now, an average cost per item, or yeah, an average cost per item is the total cost, right? In other words, what? Variable and fixed cost split over, right, the number of items. So it's simply our cost divided by X. So that's the average cost. So in our case, it would be 5X plus 300 over X. Right? Now, of course, what's the cost per item? 5. But the average cost basically does also what? So if you take this, as we just did before, and you take the 5X plus 300 and divide it by the one term, that's really 5X over X plus 300 over X. So sure enough, what this simply does is, I know it costs $5 an item, yes? But it also takes the 300 fixed cost and divides it by that same amount of items. So basically, if you produced nothing, the cost per item kind of, well, let's just say you can divide by 0. But if you produced 1 item, what's the cost per item? Well, $305 because you only produced 1 item. If you produce 2 items, what's the cost per item? It's $155. Why? Because now your 300 got split over the 2 items you produced, right? So the more you're producing, the more it will cost you, the less it will cost you per item, okay? Does that make sense? All right. So the reason why this problem is at this section is because, as you see, there's a quotient here, yes? Okay, so let's go through. So that's the average cost, right? It's you can leave it either in this form or simplified. What's the marginal cost? Remember, marginal means the derivative. So if you take the derivative of this 5x plus 300, it's a linear function, right? So the derivative is simply 5, which means that what? At any amount of items, right? The cost per item is $5 per one item, right? Even if I'd say, what's the marginal cost, let's just find marginal cost when 10 items are produced. When 10 items are produced, it's 5. Yes, so when 10 items are produced, the cost per item is increasing at $5, right? So every time you produce one more item, we're going to spend $5 more, yes? Now, what's the marginal average cost? Marginal average cost, by the way, right? Marginal average cost is simply the derivative of the average cost function. Now, what was my average cost function? Right here, 5x plus 300 divided by x. How do I take that derivative? Well, we're going to use the quotient rule. So, take the derivative of the top, which is 5, times the bottom, minus, leave the top alone, times the derivative of the bottom, which is 1, all over the bottom squared. So I'm going to simplify this for sure. So this is a 5x minus 5x minus 300 all over x squared, which is negative 300 over x squared. Okay, sorry. Now, as you see, there's an x left. So what's the marginal average cost of 10 items? That's negative 300 divided by 10 squared, so that's negative 3, which simply means what? When 10 items are produced, the average cost over all of them, right? Split over all 10 items. Because this is where we're taking the derivative of the average cost, right? So the average cost per item goes down or decreases by $3 per item And why? Because an average cost is already $1 per item. Yes, per item. Okay. So here, let's just look at this. What's the average cost for 10? We're looking at average, our cost per, right, of producing so many items, and even like the average cost. So what's the average cost of producing 10 items? It was 5 times 10 plus 300 over 10. So that's 350 divided by 10 is 35. So once you have produced 10 items, yes, the average cost per item is only $35. Why? It's $5 per item, yes, but you also took the 300 fixed cost and now split it over 10 items, right? So those 30 now, right, plus the $5 that you have to add on every time. Okay, what's the average cost of producing 11 items? Well, that's 5 times 11 plus 300 divided by 11. So I'm going to need a calculator for that. So that's going to be 355 divided by 11. So that's 32.27 per item. Okay, so as you see, what's happening? You've split the 300 fixed cost now between 11 items, so the cost per item has gone down, yes? So by about how much did the cost per item go down after 10 items? It decreased by about $3, yes, per item. It's not exactly 3, it's more like 2.73, but about, right? So remember, that just approximates it. Okay. So that's the idea here. What I would like you to do is see how we had these two formulas here. One's simplified, right? We just took the quotient and just used the quotient rule. But you could have used this form of it, to take the derivative. So what I'd like you to do is use maybe this form of it to take the derivative. See if you're also coming up with negative 300 over x squared. Okay, so this is it. This section was definitely a little bit less, and we got it all filmed into one video. All right, get on your homework now.